Welcome to the third lecture of this week. In the last lecture, we have seen the initial concepts in the linearization of autonomous systems. Today, we are going to try to complete that topic. So let us continue with the linearization of autonomous systems. In this case, we are talking about time invariant and unforced systems. So the system equation is looking like this. X dot is equal to f of x and y is equal to, I would say, h of x. And I would like to convert this system into an autonomous linear system, okay? And in that case, we will need to make some variable changes. We will define some new state variables and some new output variables. And then we're going to convert this system into a form given like this. So Z is our new state vector. So we will define some new state coordinates, and we will define some new output coordinates as well. I will call these new output variables as rho, and then this is going to be h times z. Okay? So we would like to make such a conversion. And of course, we would like to do this linearization around some operating point of the system. Usually that operating point is selected as an equilibrium point of the system. So I would take here, the operating point is going to be given to us, and we're going to obtain such equations for the system. And I want this approximation to be valid, to be accurate around the operating point. Okay? So last time we have seen the concept of a Taylor series expansion, or a first order Taylor series approximation. And remember that we have tried to linearize the system dynamics equation in the last lecture, and we have achieved to actually convert it into such a form. Today we are going to combine that analysis. First we will review that analysis a little bit, and then we will also apply the same idea to the measurement equation as well. Okay? So now I'm going to just write the main concept, first order Taylor series approximation. It is f of x bar plus, remember I have the matrix F here, and I have x minus x bar vector here. This is the first order Taylor series approximation of the function f around the equilibrium point x bar. So here let us write, we choose x bar, the operating point, as an equilibrium point of the system. Okay, and that means that f of x bar is equal to 0. All right? And we know that this approximation, this term is going to be equal to 0 due to the equilibrium point property. And what about this f? So this is equal to f times x minus x bar. So here this f is defined as the Jacobian matrix del f over del x evaluated at the equilibrium point x equals to x bar. Remember that while trying to obtain the Jacobian matrix, I am actually trying to write all components of del f1 over del x1. So the rows are with respect to the different components of f, del f1 over del x2, and the columns are for different elements of x, and that is going to be del f1 over del xn. This is the general form when f has the dimension n and x has the dimension n. The dimensions of f and dimensions of x should be equal, because you see here that f gives us x dot, so f has the dimension n, and x should have dimension n. That means that the Jacobian matrix of the function f is always a square matrix whose number of rows is equal to the number of its columns. All right? And I would have here, so in the columns, I take derivatives of the functions fi with respect to different components of x, and in the rows I change the functions fi. Okay, so I would have f2 over x1 del f2 over del xn, and this continues until del fn over del x1, going until del fn over del xn. Okay, and this is evaluated at the equilibrium point. Okay, and that gives us this equation, this approximation. F of x is equal to capital F times x minus x bar. Okay. Now let us look at the other function, h of x here. I can apply the same idea on the function h of x. Remember that there is always the condition of differentiability for us to be able to make such an approximation. If the function f is not differentiable, I will not be able to take these derivatives. These derivatives would not make any sense, or some of them would not make any sense. That means that in order to be able to apply such an approximation, these functions should be differentiable functions at the equilibrium point. Okay? So I can actually write this as h of x bar, plus I can put here another Jacobian matrix evaluated at the equilibrium point, and I have x minus x bar. All right? So in this case, h of x bar does not really have to be equal to 0. So the equilibrium point condition is only this. So this term is in general a non-zero term. And what about the matrix H? So the matrix H would be obtained by finding the Jacobian of the function H with respect to the elements of x and evaluating x at the equilibrium point. All right? So H has a number of components, which is the dimension. The number of components of H is the number of outputs of this system, and X has the number of components of X is n. So the number of columns of this Jacobian matrix would be n, and the number of rows of this matrix would be the number of outputs inside Y. These two numbers do not have to be equal. Okay? So in general, this Jacobian matrix can be a rectangular matrix. On the other hand, the Jacobian matrix for the function f is always a square matrix, while the matrix H can be in general a rectangular matrix. If the number of outputs is different than the number of state variables, that matrix is going to be a rectangular matrix. So now let us try to substitute these equations, these approximations into those system equations. X dot is equal to, I would have f times x minus x bar, and y is equal to, I have h of x bar, a constant term or zeroth order term, plus h x minus x bar. So now I'm going to make an approximation. I'm going to now make a new definitions for a new output and new state variables. So the first thing that I define is a new state variable. That is z is x minus x bar. Okay? Last time I talked about this type of definition. So if I have the original x1, x2 coordinates, suppose that the state has dimension 2, and suppose that this is my equilibrium point x bar. Okay? What we are doing by defining this new state vector is that I'm putting a new coordinate system whose origin is exactly equal to x bar. So this is the z1 coordinate and this is the z2 coordinate. So when I take any state value here, I can express this state value in terms of the original state coordinates, or I can express this state value in terms of the new state coordinates. Okay? So making this definition and using this variable z means that from this point on, I am considering my state values with respect to these new state variable x's. Okay, so this is nothing but the shift of the origin from the origin of the x1, x2 plane into the equilibrium point. So by this definition, we are shifting the origin of the state space from the origin of the x1, x2 plane into the equilibrium point. So the origin of the z coordinates would be the equilibrium point. Why is that? Because z equals to 0 corresponds to x equals to x bar, which means that the origin of the z plane would be the equilibrium point. So using this definition, I can actually try to write the first equation. So in that case, I can actually take the derivative of z, the new state vector. It would be x dot minus x bar dot. But x bar is a fixed point in time. So x bar is a constant equilibrium point and it doesn't change with respect to time. That means that the time derivative of x bar would be equal to 0. So this is just x dot. So z dot is equal to x dot and this is 0. And I know that x dot is equal to f times x minus x bar, which is z. Okay? So that gives us our new state dynamics. Z equals to f times z. Okay? So this is linearized state dynamics or state equation. All right? Around x equals to x bar, around the equilibrium point. And let us go into the output equation. Now what I'm going to do is define a new output variable. So instead of the output variable y, I'm going to define another output variable whose origin would be at this value, h of x bar. So I'm going to define my new output variable as y minus h of x bar. And just if you make an analogy with this definition, what I'm doing here is that I'm redefining the origin of my output space to be h of x bar. Okay? That is the origin of my new output space. All right? And now if I think about this equation, then I can see that this h of x bar can go to the other side, and that would give me rho equals to h times z. Okay? So this is our new output equation. All right? Or let us say linearized output or measurement equation around x equals to x bar. So you see that we could actually convert both of the equations of the system into a linear autonomous form. So then, therefore, now I actually combine both of these equations together to get the linearized system equations. So this is linearized system around x equals to x bar. Okay? And that completes our analysis. Now we're actually ready to solve some examples. Maybe before talking about the example, I maybe should tell you the thing that I have talked about in the last lecture. So remember, Taylor series approximation, it would be only valid or would be only accurate if x minus x bar is small. All right? So remember a general Taylor series expansion, so of the function f. F of x is equal to f of x bar plus del, I will write the scalar case here, d over dx of f, and evaluated at x equals to x bar, times x minus x bar. This is the first order term we always use, but there are also higher order terms. So there is an equality here. So if I include the higher order terms, in general the truncation of this series, truncation of the higher order terms would make this equation an approximation. But if I add the additional higher order terms here, there would be an inequality here. All right? So I have d square over dx square, x minus x bar square. I would also have a 1 over 2 here. And these terms would continue until infinity. So if I write the general formula for the Taylor series expansion with equality, I would have the following formula. I from 0 to infinity, I would have 1 over I factorial, and I would have the ith order derivative. So this is at x equals to x bar. Ith order derivative of the function f, the xi, evaluated at x equals to x bar, and I would have x minus x bar to the power I. So in general, our first order approximations would be valid if x is close to x bar, so that x minus x bar is small. Why do I say that? Why do I say that when x minus x bar is small, our approximation would be accurate? This is because of the following fact. If this thing is small, suppose that this is epsilon, and suppose that epsilon is a very, very small number, in that case, epsilon square would be even smaller, and epsilon cube, epsilon fourth order, would be even smaller. Okay? And that would make these higher order terms here much smaller than the first order term that we use. So neglecting these higher order terms would be a good approximation if x minus x bar is a small number. On the other hand, if x minus x bar is a large number whose magnitude is large, in that case x minus x bar is going to be that large number, but I would have here x minus x bar square, which is going to be even larger. All right? And that means that this approximation would not be valid if x minus x bar is actually a large number. That means that our approximation here, or the approximate linear autonomous system, linearized autonomous system here that we would obtain, would be only valid for small z values. Remember, z is x minus x bar. If z is small, then we know that such a system approximation would be valid or would be accurate. Okay? So this approximation in general, going from here to here, we make some approximations, and these approximations are good approximations only if z is small. If z becomes large, then this linear autonomous system might not represent the behavior of the actual nonlinear system. Okay? That is an important point to keep in mind. So now let us solve an example. I will start with a second order system. X dot is equal to x2 and minus x1 plus x1 cube. Okay? That is the definition of my f of x. Okay? And the output equation is given as y equals to x1 square. And the task is to obtain linearized systems around the equilibrium points of this system. Obtain linearized systems around the equilibrium points. Equilibrium point or points. So the first thing that I'm going to do is to calculate the equilibrium points of this system. Now, I will equate the right-hand side to 0 here, x2 equals to 0, and minus x1 plus x1 cube equals to 0. So I can here take x1 parentheses, and that would give me minus 1 plus x1 square equals to 0. This gives me three possibilities. Either x1 equals to 0, or x1 equals to 1, or x1 equals to minus 1. Okay? So this system is going to have three different equilibrium points in its state space. And these equilibrium points are xe1 is the origin, and xe2 is going to be the point 1, 0, x1 is 1, x2 is 0, and xe2 is going to be minus 1, 0. Okay? So if I show these equilibrium points on the state space, then I would have an equilibrium point at the origin, equilibrium point at the point, sorry, that's plus 1, and I would have another equilibrium point here. So the nonlinear system has three isolated equilibrium points, and the linear dynamics around each equilibrium point might be different. Okay? So we are required to calculate such linearized system approximations around each one of these equilibrium points. So the first thing that I'm going to do is to calculate the Jacobians of the function f and function h here. So this is the function h of x. Okay? Let us calculate these Jacobians. So del f over del x. So we see that f has two components and x has two components. That means that I would have a square matrix here. Okay? So I would have the first derivative of, this is my f1, this is f2. Derivative of f1 with respect to x1. You see that this f1 does not depend on x1, therefore the first derivative is going to be equal to 0. And this element is going to be derivative of f1 with respect to x2. And derivative of this thing with respect to x2 is 1. Now let us take the other derivatives. This is my f2. Take the derivative of f2 with respect to x1. That is going to give me minus 1 plus 3x1 squared. And derivative of f2 with respect to x2 is just 0. So this is the Jacobian matrix of the function f. Let us write the Jacobian matrix of the function h. Okay? In this case, what is going to be the size of this Jacobian? Remember that the Jacobian matrix has as many rows as the number of components of f, and it has as many columns as the number of components of x. Okay? So you see that here, this output is scalar. That means that the system has a single output, meaning that the function h has only a single component. That means that the number of rows of this Jacobian matrix is going to be 1, and the number of columns would be, again, the size of x here, which is just 2 here. So the Jacobian matrix of h would be a 1 by 2 matrix. It's going to be a horizontal vector. Okay? So the derivative of h with respect to x1 is 2x1, and derivative of h with respect to x2 is 0. Okay? So now we are ready actually to calculate the linearized systems. So this is really not difficult. So let us look at the case of XE1. So if we want the linearized system around the origin, then I need to evaluate these Jacobians at the origin, okay? And that is going to give me the F matrix. I would call this as F1, and evaluate the Jacobian, this Jacobian, at x1 equals to 0 and x2 equals to 0. So you see that it's going to give me the matrix 0, 1, 1, minus 1, minus 1, 0. Okay? And if I calculate the H1 matrix, in that case, I would have just 0, 0. All right? So now let us make our definitions of the new state and the new output. Z is equal to x minus x bar for the first equilibrium point, and the first equilibrium point is 0, 0. Instead of x bar, I would write here XE1. Okay? And we see that the first equilibrium point is 0. That means that Z is equal to x for the first system, first linearized system. So I don't really have to define a new state variable in this case. And what about just the new output? Rho equals to y minus h of XE1. Okay? If I calculate h of XE1, if I substitute in this h function 0, 0, I would get 0 again. So rho is equal to y in this case as well. So for the system, linearized system approximation around the equilibrium point at the origin, we really do not have to define these new state variables. So I can actually write the linearized system as x dot equals to f1 times x, and y is equal to h1 times x. Here in this case, I really do not have to use the variables z and rho, so I have just used this. So you see that in this case, something strange happened. So this can always happen actually in linearization. H1 is purely 0. Okay? So here, the linearized system, whatever its dynamics is, would always give me a 0 output. But that is actually expected because of this x1 square. Okay? It has a slope around the origin. It has a slope equal to 0, which makes this output equation in some way meaningless. All right? That is the limit of this approximation actually. If you want to approximate a parabola around the origin, if you want to approximate a parabola like this, x1, and this is x1 square, if I want to approximate this parabola around the origin with a line, the best thing that I can do is just to draw a horizontal line here passing through the origin. But that is going to be the 0 function, which is what is happening in this output equation. H1 is 0, so y is equal to 0. So the first order Taylor series approximation here is really, it would really be accurate around when we are very close to the origin, but it would be really terrible if we are far away from the origin. Okay? So a first order approximation tells us that choose the output exactly equal to 0. So that is my system dynamics. So x dot is equal to the new system, linear system dynamics would be just 0, 1 and minus 1, 0, and y is equal to 0, 0, x. So this completes the first equilibrium point analysis. Now let us go into the second one. XE2, in this case, XE2 is 1, 0. So X1 is going to be 1 and X2 is going to be 0. In this case, F2 is substitute X1 equals to 1 in this formula, then you would get just 0, 1, 2, 0. This is my F2 matrix. And what about H2? In this case, if I substitute 1 here, I would get just 2, 0. And I will look at my new state variables. Z equals to X minus XE2. Okay? And that gives me X1, X2 minus 1, 0. So we see that the new state variables, Z1, Z2, would be equal to X1 minus 1 and X2. So the second state variable would remain as the second original state variable. On the other hand, the first state variable is going to be changed into the first state variable minus 1, if we are here. So that means that I'm shifting the origin of my state space to here, to this equilibrium point. Okay? And let us define our new output variable. The output variable is going to be rho equals to, I would have y minus h of XE2. Okay? And h function is this one. So I would substitute the equilibrium point coordinates into this, which is going to give me 1. So the new output is y minus 1. So that when the new output, rho is equal to 0, that is going to mean that y is equal to 1. So this is also the shift of the output space origin to the value 1. If the new output is 0.1, then this would mean that the output in the original coordinates would be 1.1. Okay? So now we can write our state dynamics equation. In this case, I need to use z because z is not equal to x anymore. So I would have the system dynamics as 0, 1, 2, 0, z. And rho equals to the new output matrix 2, 0 times z. Let us quickly do the same thing for the third state variable and complete this example. So I can calculate F3, which is going to be the same as F2, 0, 1, 2, 0, because I have x1 square here. It doesn't matter if x1 is 1 or minus 1 to us. And then H3 is, I would have minus 2, 0 in this case. And the new state variable z is going to be x minus XE3, which is going to be different than. So z is going to be different than x because the equilibrium point is not at the origin. And the new output would be, I would have y minus 1 again. Okay. Let us write the system equations. Z dot is equal to 0, 1, 2, 0, z. And rho equals to minus 2, 0, z. This completes this example. I will solve another example which is going to be useful for us or illustrative for us later. It's a very, very famous nonlinear system example, and it is good to actually try to interpret such a nonlinear equation, which represents some environmental phenomena. So the species dynamics. So the example that we are going to solve is going to be, or the system that we are going to be working on is called Volterra predator-prey system. Or let us look at an example. This is called Volterra predator-prey system. So predator means avcı in Turkish, and prey means av. And the system equations are given. This is a second order system again. And I can write the system equations as follows. Minus b1 x1 x2. And x2 dot is equal to minus a2 x2 plus b2 x1 x2. Here, a1, b1, a2, b2 are just positive parameters of this system. So this type of system is a model or mathematical model proposed for the dynamics of the natural species in a closed environment. Suppose that we are on an island and we are looking at the number of some animal which eats another animal, and we are looking at the number of those animals on that island in time. Okay? So here, these variables, x1, it is actually the number of the prey animals, okay? So let us say this is the number of rabbits, okay? Traditionally, these are rabbits and foxes. So rabbits are tavşan, and foxes are tilki. X2 represents number of foxes. So this x1, which is obviously the number of rabbits is not a continuous variable. There are no 2.5 rabbits. But it is here modeled as a continuous variable. Okay. So a more accurate model would think about the integer numbers. But if the rabbits are too many and if the foxes are too many, then they are taught here like continuous valued variables. The task is to do the same thing. Obtain linearized systems around the equilibrium points. Okay? So the first thing that I'm going to do is to actually explain you why this model would represent such the dynamics of the number of some animals here on an island which is inaccessible to, let us say, humans. The first thing that I will talk about is this. If you have a scalar x, and if you have the differential equation x dot is equal to ax, how can you solve such a differential equation? This is a linear first order differential equation. Then suppose that somebody gave us the initial condition, x0 is equal to a number, x0. And what is the solution in this case? So here, as engineers, I would expect you to be able to solve this type of differential equation by inspection without making any calculations. Before you graduate from this department, know how to solve such a differential equation in terms of the initial condition and A. Okay? So here I will just write the solution. Here, this is a first order differential equation, and x of t in this case is going to be e to the at times the initial condition. Okay, x0. So this is my solution for t larger than or equal to 0. So you see that this is a first order system and the response is exponential. If A is positive, what is going to happen to x of t? Whatever x0 is, the solution magnitude is going to diverge to infinity. Obviously, I'm assuming a non-zero initial condition here. Okay, suppose that x0 is non-zero, and in that case, if A is positive, whatever x0 is, absolute value of x of t is going to go to infinity. And it's going to diverge to infinity exponentially. All right? So what about the case when a is equal to 0? In that case, the differential equation turns into x dot is equal to 0, and that means that x of t is constant, which is equal to x0 for all t larger than or equal to 0. And what happens if a is strictly smaller than 0? In that case, we see that this exponential is going to decay to 0 exponentially fast. Okay? And that means that the magnitude of x of t is going to converge to 0 as time goes to infinity, or converge to 0 to exponentially fast. Okay? So this is this type of differential equation. So you see that here, if I neglect these terms here, both of these differential equations have this form. Okay? Have this form. All right? Now let us try to understand what happens if we don't have these nonlinear terms here. I know that all of these coefficients are strictly positive, so B1 is positive, B2 is positive. But I am here looking at a hypothetical situation where both B1 and B2 are equal to 0. Okay? Suppose that these are equal to 0. In that case, what would these dynamics mean? x1 dot is equal to a1 x1, and x2 dot is equal to minus a2 x2. Okay? So here we see that the differential equation for rabbits, number of rabbits, has a positive a coefficient here. Okay? On the other hand, the differential equation for the foxes would have negative a coefficient. Okay? So if these, and you see that these two differential equations are independent of each other. All right? So we have decoupled dynamics. When these two species, if they are not interact with each other, the interaction comes from these coefficients. Why is that? Because x1 dot is a function of x2 here, as you see. This is the interaction, this term represents the interaction of rabbits with the foxes. On the other hand, this term in the second differential equation represents the interaction of the foxes with the rabbits. Now I'm removing these interactions by assuming B1 and B2 are both equal to 0. In that case, what is happening? So I see that in this case, x1 of t is equal to, I would have x1 0, initial number of rabbits, e to the a1t. a1 is positive, so when there are no foxes, okay, so when the foxes and the rabbits, if they do not interact, I see that, so that means that foxes will not be able to eat rabbits. So I see that x1 is x1 0 times a growing exponential, okay? That means that if the foxes do not eat rabbits, then it is the removal of this interaction. Then what is going to happen is that the number of rabbits is going to increase exponentially. Okay? Of course, we are assuming here the food source, which is the greenery, it is infinite. Okay? So assuming that the food sources are infinite on the island, the number of rabbits will grow to infinity if the foxes do not eat them. And what about the second one? So if the foxes do not eat the rabbits, then the number of foxes is going to be the following: x2 0 e to the minus a2t. And I know that this is going to decay to 0 exponentially fast. So if there is no interaction between the foxes and the rabbits, then the number of foxes, it is going to decrease exponentially to 0. All right? So it was only this part of the dynamics. Now let us try to understand what would the addition of these terms would represent. So in this first equation, A1 x1 minus B1 x1 x2 here. Okay? So here the right-hand side is the rate of change of the number of rabbits. Okay? If the right-hand side is positive, rate of change of the rabbits would be positive. So the number of rabbits would increase. And if the right-hand side is negative, then the rate of change of the rabbits would be negative, which means that the number of rabbits will decrease. Okay? So here, I know what happens without this interaction term. The number of rabbits, this would be always positive if the initial condition is positive. So the number of rabbits will grow. But this term, this type of interaction term, is going to decrease the rate of change of the rabbits. Okay? So you see that this term can actually balance such a positive term if x2 is very large. So this term represents the fact that the foxes are going to eat rabbits. And if there are more foxes, if x2 is large, then what is going to happen is that this term is going to dominate this term, and the rate of change of the rabbits would be negative. And that means that the number of rabbits will decrease. All right? And here you see there is another term related to x1. If x1 is large, this decrease is going to be much more. Okay? Why is that? Because if there are too many rabbits, then if x1 is large, then they're going to compete for the food source. Okay? Compete for the food source, and therefore if there are more rabbits, actually we are going to see the decrease in the rate of change will be more. So the number of rabbits might decrease in a faster way. All right? So now let us look at the dynamics of the number of foxes. x2 dot is equal to minus a2 x2 plus b2 x1 x2. In this case, I know what happens when there are no coupling between the systems. The number of foxes will decrease exponentially fast because they cannot find any food without the rabbits. But here this term would bring us the interaction between the number of foxes and the number of rabbits. And here you see that if the number of rabbits is large, if x1 is large, we see that this negative term, which decreases the number of foxes, can be positive if x1 is very, very large. Okay? If there are if there are many foxes around, if there are many rabbits around, then the foxes will eat them, and they are going to escape extermination at the end. Okay? So their numbers can increase if there are lots of food which are rabbits around the island. Okay? And here you see that this rate of change would be further increased if x2 is larger as well. So if the number of foxes is large, then the rate of change of the number of foxes would also increase. Why is that? This is representing some form of teamwork. If there are many foxes, then they might form some teams maybe. I don't know what its name in English. So fleet, no, not. Anyway, it's English knowledge, not related to nonlinear control. If x2 is large, then they might actually form some teams to hunt the rabbits, and it's going to be better for them. Their number might increase. So this is the Volterra predator prey system. Okay? So now let us try to find the equilibrium points of this system. Okay? So the equilibrium points are going to be found by equating the right-hand side to 0. x1 minus b1 x1 x2 equals to 0. And minus a2 x2 plus b2 x1 x2 equals to 0. All right? If I take x1 parentheses on the left here, a1 minus b1 x2 equals to 0. And if I take x2 parentheses here, minus a2 plus b2 x1 equals to 0. If I find the solutions here, x1 equals to 0 and x2 equals to, let me say, a1 over b1. And this is x2 equals to 0. And I would have x1 equals to a2 over b2. So now from these solutions I can actually find the equilibrium points of this system. Now here, remember that both of these equations have to be satisfied at the same time. Okay? So you see that if I take x1 equals to 0 and x2 equals to 0, that is going to be an equilibrium point. So I have 0, 0. This is the first equilibrium point, xe1. Okay? So can I take these two? x1 equals to 0, x1 equals to a2 over b2. Definitely, these two equations cannot be combined. So this is a non-zero number, this is 0. On the other hand, if I take this value and this value, I would get another equilibrium point. xe2 is equal to, I would have a2 over b2 and a1 over b1. So this system has only two equilibrium points. We see that I cannot combine these two either. So we have only two equilibrium points. What do they look like in state space? This is x1, x2. So the first equilibrium point is here. Total extinction. So there are no rabbits, no foxes on the island. They all went extinct on the island. So this is our first equilibrium point. Definitely, if I start the system with 0 foxes, 0 rabbits, then nothing is going to happen, no dynamics. So this is my first equilibrium point. And the second equilibrium point is somewhere here. So I have a2 over b2 and a1 over b1, and this is something environmentally much better. So there are a number of rabbits and a number of foxes on the island, and they are in some form of equilibrium, their number. All right? So now we're wondering about the system dynamics around these equilibrium points. Okay? So the first thing that I'm going to do is to calculate the Jacobian of that function f. So del f over del x is going to be derivative of the first function with respect to x1, and that would be a1 minus b1 x2, and derivative of that function with respect to x2 minus b1 x1. Derivative of the second function with respect to x1, b2 x2. Derivative of the second function with respect to x2 minus a2 plus b2 x1. Okay? So this is my Jacobian, and let me now try to, so in this case we are only given the state equation, so I don't have to deal with the output equation at all. And as a result, I need to just calculate my Jacobian matrices evaluated at the equilibrium state. The first equilibrium is 0, 0. Substitute x1 equals to 0 and x2 equals to 0. In that case, you would get a1 minus a2 and 0, 0. This is my first F matrix for the first equilibrium point. And the second F matrix for the second equilibrium point would be substitute x1 is equal to a2 over b2. So if I substitute x1 equals to a2 over b2, so here you see that this is going to be 0. Okay, and I will substitute x2 equals to a1 over b1. If you do that substitution here, you would get 0 here. And this one is minus b1, and I would have a2 over b2. A2 over B2, and this one it would be B2 A1 over B1. Okay, I have two F matrices for these equilibrium points. So now let us concentrate on the first equilibrium point around the origin. So for the first equilibrium point, Z is equal to x minus xe1, and xe1 is equal to just 0, the origin, so Z is equal to x for the first equilibrium point. And that means that my new dynamics is going to be Z dot is equal to F1Z, or Z dot is equal to, I would have A1 minus A2, 0, 0, Z. Okay? And for the second equilibrium point, Z equals to x minus xe2, and xe2 is different than the origin. That means that Z and x are different variables in this case. But what I have to do here is to write the dynamics around xe2, and that would be Z dot is equal to F2Z, and we see here that Z dot is equal to F2 in that case would be 0 minus B1 A2 over B2, and B1 A1 over B1, sorry, B2 A1 over B1, and I would have 0 here times that. Okay. So these are the linearized system around these equilibrium points. Okay. So here in the future parts of this course, we are going to analyze the trajectories of the nonlinear system around its equilibrium points. Okay? We are going to analyze the trajectories of the nonlinear system around the equilibrium points. Okay? So how are we going to do that? We are going to do the analysis of those trajectories by looking at the linearized system dynamics around those equilibrium points. So this is the linearized system dynamics for the first equilibrium point, and this is the linearized dynamics around the second equilibrium point. Okay? So we are going to see that when we look at these matrices, we are going to be able to tell really a lot about the trajectories of a nonlinear system around the equilibrium points. Okay? And what do we mean by looking at these matrices? Actually, the thing is going to be that when we look at the eigenvalues of such matrices, we are going to be able to tell really a lot about the behavior of the trajectories of the system around each of those equilibrium points. And when I look at such a 2 by 2 matrix, it is a diagonal matrix. As a result, its eigenvalues are going to be the diagonal elements. So I see that here, the first eigenvalue is positive, and the second eigenvalue is actually negative. Okay? In that case, I would see that the behavior of this nonlinear system around this equilibrium point is going to be something like this. Okay? So I would have a decrease in the second state variable, and the first state variable is going to increase. You don't really have to understand this type of behavior now, because we are going to see this in detail. I'm now just trying to illustrate what we are going to do in a future part of this course. And when I look at the behavior of this system around this equilibrium point, and we are going to look at the eigenvalues of this matrix. In the first case, eigenvalues are real, and one is positive and the other one is negative. Okay? We are going to classify such equilibrium points as saddle points. The meaning is going to be made clear when we see such topics. So since the eigenvalues of this matrix are real, around the first equilibrium point, we will never see oscillations. Real eigenvalues, it is going to mean no oscillations. We will just have decreasing behavior. And you see that this type of behavior is nothing but a pure decrease in x2 and a pure increase in x1. Okay? On the other hand, when we look at the eigenvalues of this matrix, we are going to see that they are going to be complex. And in this course, just like the course, the EE404, your third year control theory course, the complex eigenvalues would mean oscillations. So that is going to mean that this system around the second equilibrium point, it is actually going to oscillate. There are circular or closed trajectories around the equilibrium point where the variables are going to oscillate in a periodic motion. Okay? What does this mean? This means that if this system is started somewhere close to this equilibrium point, so suppose that I start the system like that. Suppose that I own the island and I put there some number of rabbits and some number of foxes. So I start the system somewhere here. Okay? The number of rabbits is this, the initial number of rabbits, and this is the initial number of foxes. If I start this system here, you see that there are really few rabbits and there are too many foxes. That means that the number of rabbits will not be really sufficient for the foxes. Okay? So the number of foxes would decrease, and while the number of foxes is decreasing, the number of rabbits is going to start to increase. Okay? And then there will come a point when there will be too many rabbits here and too little foxes. Then foxes will realize that there are really lots of food around and they are going to eat these rabbits, and the number of foxes is going to start to increase. Okay? While the rabbits are continuing their increase here. So there is going to be some point when there are too many foxes now. Okay? And then what is going to happen is that these foxes will eat these too many rabbits, and the number of rabbits is going to decrease quite fast. So the system is going to oscillate. So both of the variables are going to be in oscillation in time. If I start the system very close to the equilibrium point, we will observe from this in the system some oscillations in both of the variables. This is actually what is happening in nature always. Okay? So this system, although it is very simple, it can really predict some physical behavior or some environmental behavior that we see in nature. So for example, a question might be, what would be the frequency of this oscillation? Okay? Or what is the amplitude of that oscillation, etc. In this course, in the future parts, we will be able to answer such questions as well by making or applying some more analysis on this type of nonlinear systems. So far we have seen this concept of equilibrium points and the linearization for autonomous systems. Remember, we have also seen the concept of equilibrium points for time invariant systems. And that is the only topic remaining in this part of the course. And afterwards, we are going to try to draw this type of trajectories. The only topic remaining in this part of the course is going to be the linearization of time invariant systems. What happens when we, in addition to the system equation like this, x dot is equal to f of x, y is equal to h of x. Suppose that my system is not autonomous. Suppose that it looks like this. F of xu and y is equal to h of xu. So when the system has an input, how can I linearize such a system? Again, we're going to use our equilibrium point theory, and we will be able to get linearized system dynamics and measurement equations for that type of systems. But that is going to remain for the next lecture. That's going to be all for this one. Thank you very much for watching. Bye.